So welcome back to Logic, Language and Information. In this lesson we'll continue to work with truth tables to make logical assessments, here looking at relationships between propositions rather than classifying single propositions as we did last time. For many applications of logic, we want to know about relationships between propositions. In assessing the validity of an argument, the key logical relationship is that which lies between the premises and the conclusion. In the linguistics application section of the course, we will be distinguishing between logical entailment and a somewhat weaker form of connection called an implicature, which occurs often in everyday speech. These implicatures can be understood in terms of logical entailment after making explicit all implicit assumptions and background knowledge. In the digital electronics application section, we will see how a propositional logic formula specifies a digital circuit, and we'll be interested in seeing when two circuits do exactly the same job by showing that their propositional formulas are logically equivalent. First, the notion of logical consequence. A formula B is a logical consequence of a formula A exactly when, for all truth valuations in which A is true, B is also true. We write this with a double turnstile symbol. So A double turnstile B can also be read as A logically implies B or A logically entails B. And we will use these phrases interchangeably. The relationship requires a truth transferring directed connection from A to B. Where have we seen this before? Yes, it is indeed the same idea as that in the semantics of the material conditional. But while a conditional formula may be true or false on various rows of its truth table, the relationship A logically implies B requires that truth transfer occurs for all possible truth valuations to the atoms in A and B. A conditional proposition is true or false as a matter of fact, while a logical consequence relationship is a different beast. It holds in virtue of the logical structure or shape of the formulas together with the meanings of the connectives within them. In terms of a truth table, the truth transfer connection from A to B requires that for every row of the truth table in which A gets value 1, we have B also getting value 1 on that row. For example, consider whether P and not Q logically entails not P or not Q. Of the 4 rows of the truth table, there is only one in which the first formula, P and not Q, is true, namely the third row. So we only need to check this row to see that the second formula, not P or not Q, is indeed true on that row. That is all that has to be checked to confirm that yes, indeed, the first formula logically entails the second. In the other 3 rows where the first formula is false, we don't have to check anything because there is no requirement for falsity transfer, just truth transfer. What about the other direction? Does the second formula, not P or not Q, logically entail the first? Well, no, because on the first 2 rows of the truth table, the second formula, not P or not Q, is true, whilst on those rows, the first formula is false. So this shows that not P or not Q does not logically entail P and not Q. The bidirectional two-way version is called logical equivalence. Formula A is logically equivalent to B exactly when, for all truth valuations, A and B evaluate to the same truth value. The symbol used here is the forwards-backwards two-way double turnstile. In earlier lessons we have already discussed some logical equivalences, where two formulas have exactly the same column of truth values under their main connective. The De Morgan's laws give A or B as logically equivalent to not A and not B, and dually A and B is logically equivalent to not A or not B. The meaning of the material conditional is expressed in the logical equivalence of if A then B with not A and not B, and also with not A or B. Logical consequence, logical equivalence and tautologyhood are related as follows. First, the two-way is 2 times the one-way principle. A is logically equivalent to B if and only if A logically implies B and B logically implies A. Second, logical consequence can be expressed in terms of tautologyhood for the material conditional. A logically implies B if and only if the conditional formula if A then B is a tautology. This is a feature that distinguishes classical logic from some non-classical logics. In this logic, we have a connective that exactly captures our notion of logical consequence. While in some other formal logics, the logical consequence relationship cannot be represented by a connective of the base language in this way. Third, logical equivalence can be expressed in terms of tautologyhood for the biconditional. A is logically equivalent to B if and only if the biconditional formula A if and only if B is a tautology. The phrase if and only if is often abbreviated by the letters IFF. Now for an exercise. Suppose A and B are some complex propositional formulas built out of the atoms P, Q and R. And their truth tables, with the main connective for each formula, comes out as shown on the table here. So which of the 4 stated options are correct? Is A logically equivalent to B? Or option B, is A logically entailing B, but B not logically entailing A? We use a slash through this entailment symbol to indicate negation. Option 3, B logically entails A, but A does not logically entail B. Or option D, none of the above. How did you go? So the columns of truth values for A and B are identical except for the second row, when A is true and B is false. What this second row shows us is that A does not logically entail B. Then there are 4 other rows in which B is 1, and on those rows, A is also 1. There is an absence of any row in which B is 1 and A is 0. So that together shows that B logically entails A. So the answer is C. As a quick variant, suppose we had the same table, but except for the last row, where we change the B value to 1 rather than 0. Then ask the question again, what relationship holds between A and B? In this case, we would actually end up with the answer D, none of the above, because this additional last row would show us that we do not have B logically entailing A. So we would have A not logically entailing B and B not logically entailing A, so the answer is none of the above. If you have more questions or comments, then, as usual, take a look at the course notes first and head into the discussion boards to express your views. Logically equivalent formulas have precisely the same truth values under all valuations to atoms. The opposite notion is that of logical contradictories. A and B are logical contradictories exactly when, for all truth valuations to their atoms, A and B come out with opposite truth values. This requires B to be false whenever A is true and B to be true whenever A is false. For example, if P then Q is logically contradictory with P and not Q. Write that down. If P then Q is logically contradictory with P and not Q. So a question, how could we express the property of two formulas being contradictories in terms of the notions of logical equivalence and logical consequence? The answer is fairly straightforward. For any propositional formulas A and B are contradictories exactly when A is logically equivalent to the negation, not B. And this is true exactly when the biconditional A if and only if not B is a tautology. The medieval logicians used two further logical relations, that of being contraries and subcontraries. Formulas A and B are contraries when they cannot both be true together. So B is false whenever A is true, and A is false whenever B is true. The other notion of subcontrary replaces the cannot both be true with cannot both be false. So A and B are subcontraries if B is true whenever A is false and A is true whenever B is false. For example, the formulas not P or Q compared with P and Q. The column under the main connective evaluates as 1, 0, 0, 0 in standard ordering for the first formula compared with 0, 0, 0, 1 for the second. So that tells us that they are contraries, but they are not subcontraries. Furthermore, neither formula logically implies the other. Now, how can we express this relationship, the contraries and subcontraries relationships, again using our fundamental notion of logical consequence? The following result characterises these traditional logical relations. A and B are contraries if and only if A logically implies not B, while A and B are subcontraries if and only if not A logically implies B, and this in turn is the case if and only if not B logically implies A. So subcontraries can be seen to involve the converse logical implication of that holding of contraries. This brings us to the end of this lesson on the logical relationships between propositions. The core of the lesson is the central relationship of logical consequence from A to B can be shown to be the same as having the material conditional formula if A then B being a tautology. In the next two lessons, we address the validity of arguments, which can be seen as an instance of the logical consequence relation that holds between the conjunction of the premises and the conclusion of the argument. We're also going to be looking at the soundness of arguments, where soundness is a stronger condition than validity. So see you next time.